it added there. And so the IR wavelengths will give you information about the functional groups that are present in the molecule. Okay? You do not need to memorize the exact, say, at 3,300, the bend of the alcohol's there. I mean, there's one exception. I want you to recognize a couple of features that can be on the spectrum, and that'll make more sense to those of you who are in the lab after you get in there and start to do this tomorrow night. But it does. The IR portion of the spectrum gives you information with respect to the functional groups that are inside a molecule, or that are inside, that make up part of a molecule. All that, but hopefully we got that down. And like I said, we will go back over the introductory part where I have it listed and we review what E equals H nu and C equals lambda nu mean. But the important thing here is that each of those wavelength ranges gives you a little bit different information. So the radio frequencies, right, radio waves, is the same thing as NMR, which is nuclear magnetic resonance spectroscopy, and it has to do with the flip of the nuclei, like the spin, like if it spins one way or the other. And little side note, has anyone ever had an MRI done? So that's magnetic resonance imaging, you go in that and it makes all that noise, clack, 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 it's really horrible. But especially if you are, claustrophobic, which I'm not, but, I have to go and get it done periodically. Well, the thing of it was, when it first came out, it's just a big NMR machine, okay? But people got scared because it said nuclear magnetic resonance imaging, and so they just dropped the nuclear part. But it's the same thing. So it's just a big radio frequency thing. So just a little side note. But the IR looks at the vibrational states. So I actually have to go back. And so the region that's most useful fall in the region of the IR spectrum that's between 2.5 and 16 microns, or micrometers. And they like to use a term called the wave number, which is inverse centimeters. You don't have to memorize those, but that's between 625 and 4,000. But that's just a portion of the IR spectrum. And in particular, the bonds in a molecule are not static. They're dynamic. They move around. We've talked about like little propellers and stuff, and there's movement within those bonds, and they vibrate. And so when you hit the certain wavelength in the IR spectrum, you can affect the way those bonds stretch and the way that they bend. And each functional group is a little different. So you could, without even knowing this, or without even knowing specifically thinking about it, you already know this with respect to like double bonds and triple bonds. You can't, if you got a double bond, you can't flip it around easily because the fact is it's two bonds, or in triple bonds even worse. Whereas a single bond, between two carbons, there's a lot more rotation and movement there. And so if we just imagine that we have this is called a methylene group, but it's a CH2 group. So that carbon in the middle, this carbon in the middle right here, is making a bond to two hydrogens and a bond to two other carbons, and presumably those two carbons are making bonds. They'd have to be making bonds to other things, but we're only looking about the tetrahedral state of that middle carbon. And there are two ways in this plane to stretch that CH2 group. You can either stretch it sort of like milking a cow, where you're pulling down, I guess, on it, or you can, which would be symmetric, or you can do it asymmetrical, as one is being pulled, the other end, like between the other hydrogen being pushed towards that carbon. You can also bend it, and so you could either bend it two directions out of the plane, meaning bend both of these out towards you, or bend both of them back away from you. Okay, so there's bending that's involved in stretching, and different parts of the spectrum affect stretching versus affect bending. Okay, and like I said, this will look a lot different being bent and stretched than, say, a carbon-carbon double bond or a carbon to oxygen double bond. And it's these unique characteristics that makes a spectrum. And a part of that is even called the fingerprint, because it is unique to every compound. And so, I mean, it's unique enough that it can be used for forensic science. And so, for those who've had me for forensic science, we talk a little bit about IR, but we really just call it like the chemical fingerprint. And so we don't actually, well, we never had the opportunity to do IR anyway. We just bought our IR spectrophotometer this summer. So please don't break it. We actually have a nice one. It's a diamond IR. Okay, so we can also bend it within the plane where you're bending them like away from each other, the two hydrogens. That's what this is trying to show. Or you're bending them in the same direction. And all this would be for the methylene group. Okay, so that being said, this is what it's going to look like on the, this is for what's called FTIR, for a Fourier transform. It's just a mathematical way that they measure and that they view what the bending and the stretching that's occurring. They didn't show the y-axis here, but this would be percent transmittance, presumably, because it's going down. This far right-hand region, so at really low wave numbers, that's the fingerprint region. So you should be able to point out the fingerprint region. Let me see if I can make it. So right, that just general area here would be the fingerprint region. And it's unique to every specific compound. Okay. And so then this region, which is already marked, is due to more of the stretching. This one's due to the bending portion. But if we looked at hexane versus, I think hexene is one that's coming up next, you should be able to see the difference between these two. Okay, so if we look at where the stretching is occurring in the alkane, and the bending for that matter, and so you look to see right about where it's occurring at, so near 3,000, but once again, don't memorize the numbers, please. Oh, whoops, I thought I had them back and forth, but I don't. Sorry about that. But they're going to show you, this is what I meant by the numbers, is if it's a carbon-hydrogen sp hybridized, so that's from an alkyne carbon, see, it's much further or much higher in the wave numbers, further to the left, than if it's all the way down to, you know, one that's tetrahedral. And so, once again, don't memorize those numbers. What you do is you take the spectrum, and then there are actually like libraries that you would look it up, and you would say, okay, this matches this type of compound. Or I would give you a table like this, and there's only one exception. There's one functional group that I want you to recognize because it's very unique, and you'll be able to point it out quite easily, and that's the alcohol. Okay, so this was hexene. I wish I would have put the hexene and hexane right next to each other. And so if you remembered, the hexane looked one way, and then this one, we actually see a difference. So we have this little peak right here that wasn't there before. The numbers would be shifted somewhat. And then the fingerprint region is completely different. I mean, it doesn't look the same whatsoever. And believe me, this is blown up because they modified the y-axis. And so you can see here, once again, that you'd be given this table. If I asked you to identify, I would just expect you to be able to utilize that table and say, okay, we see the peaks right around 2100 versus if it was around 1600. And so it's an alkyne versus an alkene. And we got kicked off once again. Right whenever it got to the point where it had been thinking. Okay, but we can see that, once again, you'd be giving, and on this page number will be incorrect because it's from a previous edition of the book. But it's still going to be within the same chapter. Okay, but once again, don't get lost on the numbers. Do not memorize those. Okay, there's the oxygen ones and the nitrogen ones. But it's the alcohols that I want you to recognize, because the alcohols look very, very specific. This is the alcohol. And so if you look right around 3,300 or so, like on this end, you'll see this large curving, dip. That's indicative of an alcohol. Carboxylic acids also do something similar to that, but the alcohols, and water, by the way, looks really huge because it's just an H with an OH, right? So, I mean, it usually goes really big. And so if it has this, then you can state it's an alcohol. So this one right here is 2-hexanol versus, before I do this next, let me just double check. Yes, it is next. So that's 2-hexanol. But then what happens? This is 2-hexanone, and so the only difference is it's no longer an alcohol. It's a, what functional group is this? To review your functional groups. Pardon? It's a carbonyl, but what carbonyl specific? What is it? Someone said it. Say it with some.
Ketone.
It's a ketone. And so, but it no longer has that big dip right there. It's got the sharp peak, but it doesn't have the big dip. And so that's why we can tell that if I gave you these two, I would expect you, I'd say, okay, these are the two IR spectra. One of them is 2-hexanol. The other one's 2-hexanone, a ketone. I would expect you to tell me, okay, match the one that was the alcohol because it has the big dip. Okay, and so that's pretty much the extent of the part that I want you to know the fingerprint region. This is the fingerprint region, and then where the alcohols are. Otherwise, I'd give you the table and have you match it up and say, okay, this one's got the peaks for the alkene, this one wouldn't, or this one's got the peaks for an amide, and this one doesn't. Of course, you still have to know what your functional groups are in order to do well. But are there any questions right now over IR? Yes?
Just like bending and stretching, I'm confused. Like, how do we tell, like, what do we need to know about that?
So I just want you to know that IR affects the bending and the stretching, okay? And so that's just a little bit of the theory behind it, but I'm not expecting you to know, okay, this peak right here is due to the, the bending of the carbonyl bond. Yeah, you don't need to know that. Yes.
It's like a general trend that the bending will be closer to like the fingerprint area and the
Right.
more on the okay.
Just in general. But once again, I would never ask you specifically, okay, what's this peak go to? Not for this. For NMR, you're going to find out, because you're going to learn, it makes a little bit more logical sense, you're going to learn about the placement of the NMR peaks, okay, and how to determine structure from that. This one will just tell you not so much what the structure is, like in the order, but it'll tell you what functional groups are present. And so that's why a lot of times they like to use NMR along with IR. The IR will tell you what the functional groups are. The NMR will tell you where they're located at, but it doesn't necessarily tell you what the functional group is. And so that's why they go hand in hand together. And so, all right. So I'm going to go ahead and I'll end class with prayer. And then this is just to show you once again that you can even tell somewhat, this is out of order. So just ignore this one. I'll have to throw this one out because this one is for NMR. Okay, so the IR ended